Do you remember a time before the coronavirus when instead of getting out of bed and directly into the home office, we would all cram into our cars just to sit in traffic jams for hours? Wouldn't these times be spent way more productively in self-driving cars? You could get your emails out of the way during your commute to work. But then there's headlines like this one that don't exactly inspire trust. So today we are going to unpack some of the challenges self-driving cars are facing. And we're going to do this in a way scientists love to do. We're going to simplify. So here we have a robocar, and here we have a cube. And we're going to teach robocar how to recognize this cube. Robocar uses cameras and depth sensors to try and recognize the cube, but because of inevitable measurement errors, it doesn't see this nice, clean cube, it sees a distorted thing. It's looking for a nice and clean cube, so seeing this distortion, it concludes there is no cube to be seen. And this is a point where we started our research asking, can mathematics help to recognize the cube? We're going to borrow a setting from physics here. There's a glass with some ice cubes, and over time, these ice cubes melt and we end up with some nice and cool water. That is to say, the temperature in the glass is averaging out. And it's exactly this process of averaging that we're going to use in order to get back to the nice and clean cube. So here's our setup. On the bottom right, you see the target where we want to end up with, the nice clean cube. On the upper left is where we start, this distorted cube that robocar saw. And we're going to apply this averaging to the surface of the cube. And it's looking good. The bumps are being reduced. It's getting nicer and cleaner and better. Just give it some more time. And okay, this is, I guess, enough. Okay, you can stop. Stop it, algorithm. Oh boy. Okay, this is not a cube. This is a ball. I guess we should have told the algorithm about corners and edges because those are the signals, the part that make a cube, the ones that we care about, and that should not be averaged out. In our research, how to find them, we put spikes on the cube at a 90-degree angle. Those are called normals in geometry processing. And by looking at how normals change from one side of the cube to the other, by looking at this change, we can see should there be an edge or a corner that's not to be touched by the algorithm. As mathematicians, the research result here, of course, is a formula that relates these blue normals and the red signals. But instead of describing this in detail to you, let's rather see it in action, shall we? So same setup as before. On the upper left, we have our distorted thing. On the bottom right, the target, the clean cube. And I'm going to show you the errors in red now, so you can follow the distortion. And you see that over the first couple of iterations, already the distortion is going down and down. We see less and less red. And given some more time, we actually arrive at this nice clean cube. Great. Is this a scientific success story? In a way, yes, it is. Robocar can recognize the cube now. I got my PhD. Great. But we knew what we were looking for all along, namely a smooth object with just a bunch of corners and edges. So let's go to a more realistic scenario. Robocars driving down a slightly nice and curvy road, and oh, watch out, a giant rabbit. So Robocar starts running its algorithm on this one, and depending on how long the algorithm runs, the rabbit might look like this or like one of these two versions. When you look at the rabbits, you see that given the time the algorithm runs, noise is actually going down, which is good. We want that. But focus on the ears of the rabbits for a bit. You see that the details in the ears are also going down. So we see less and less signal of the rabbit. And this is my main take-home message to you guys. We cannot reduce noise and simultaneously keep a sharp signal. And that's a fundamental problem of these methodologies. That's something that new algorithms, better scanning devices, new math will simply not be able to solve. That's a piece of knowledge we have, and a piece of knowledge we have to take into discussions on where to go with this technology, into discussions whether we want to replace imperfect human drivers by imperfect mechanical ones. The mechanical ones will make not the same errors as the human drivers do, but they will make errors nonetheless. So it's really important that we have this debate on where to go with this piece of technology. But I hope that after this talk, you enter this debate in a more informed manner. And with that, I'd like to thank you so much for your kind attention.